Okay, so it's important for us to understand that the reaction rate expressions that we've written so far, while useful, they are somewhat limited. And if we look at this plot, the red line in this plot, notice that its slope is changing, it's curving. And so the rate of that reaction is changing as the reaction goes forward. And it's changing because the concentration of the reactants in this particular reaction are decreasing. And as that reaction, the concentration of those reactants decrease, the rate of the reaction will slow down or decrease as well. And that plays into what we know already about how fast chemical reactions occur, because we said that concentration was an effect. Whenever we talked about the idea of collision theory, we said that lower concentrations tend to produce slower reaction rates. And so we see that very clearly here, and that makes this type of an analysis somewhat limited. It's important, very important to some, but the idea of something called the rate law is actually going to tell us a little bit more and be a little bit more helpful generally as chemists. All right, and so the rate law will tell us something about how the rate of the reaction changes with concentration as opposed to time. All right, and so the reaction here, hydrogen plus ICl to produce iodine gas and hydrogen chloride. We can write what's called a rate law, and that's an expression for the rate that is dependent on concentration as opposed to those time expressions that we saw earlier for rate. And here you'll notice that the rate of the reaction is equal to the product of the concentration of the two reactants, hydrogen and iodine monochloride, ICl. You'll also notice that there are exponents there represented by m and n. Those exponents are what we call the order of a chemical reaction, the kinetic order, and it's going to give us an idea of how important those particular chemical compounds are to the rate of the reaction. We also have a K, a constant there that we're going to call the rate constant. Rate constant is a very important value to understand. Small rate constants mean that the rates of those reactions are generally small, while large rate constants will indicate that the rates of those reactions are particularly large or fast. And so the rate constant will be determined for a particular reaction. It will remain constant for that particular reaction. Now, so if we think about this, all right, those orders of the reaction tell us something very important about how the concentration of a particular analyte, how important that is to how fast the reaction will react. How big of an impact will it have on the reaction rate? If the order is 1, it's called a first order reaction. All right, that means that the exponent that we would see in that rate law for that concentration would be raised to is 1. That'd be first order. If the order is 2, it's a second order reaction. All right, so the exponent that we would see above the concentration would be a 2. It'd be second order. And know that each concentration of each reactant that's in the rate law will have its own order. So one of them could be 1, the other could be 2. One of them could be 3. It could be a third order reaction. Something that we haven't touched on here is that the order can actually be 0. It can be what we call a 0th order reaction. And they can go up even from there. So it can be 0th, first order, second order, third order, fourth order, fifth order. It just depends on the particular reaction. But normally what we encounter are first, second, and third order chemical reactions. Those will be the ones that we're going to touch on. Now notice that the order of the reaction doesn't have anything to do with the stoichiometry of the reaction. And we're going to see one in a second where it's going to look like it might, but in reality, the stoichiometric ratio has nothing to do with the order of the reaction. So in this particular reaction, methyl acetate's reacting with hydroxide ion to produce an acetate ion and methanol. This is something that we'd call a hydrolysis reaction. We were going to perform this during our aspirin, the first week of our aspirin synthesis in the lab, but we were not able to do that. The rate for this particular reaction, or the rate law, is equal to K, the rate constant, times the concentration of methyl acetate to the first power. It's a first order reaction in terms of methyl acetate, times the concentration of hydroxide ion to the first power. It's also a first order reaction in terms of hydroxide ion. Now, you might say methyl acetate has a stoichiometric coefficient of 1 and hydroxide ion has a stoichiometric coefficient of 1, and so these 1s in the rate law expression that are the exponents, that are the orders, might come from that, and in reality it's just happenstance that it happened that way. It's coincidence. It does not have to be that way, and generally it does not follow the stoichiometry at all. So the stoichiometry doesn't tell us the order. So if the order is not related to stoichiometry, then how is it that we might be able to determine it? And it turns out that it's experimentally determined. You have to determine the order of the reaction experimentally. It's not something that we can know just from looking at the chemical equation. To do this, we generally need to know instantaneous reaction rates whenever the time equals 0. And so those instantaneous reaction rates can be difficult to determine. You're not going to have to determine what they are, but you're going to have to use initial rates in order to figure out what the rate law would be. We're not going to do that in this video. It's a little bit of a complicated calculation, and so I want to give it its own day, actually. So on Wednesday, you're going to see that calculation. So that's rate laws. That's an introduction to rate laws. You have an idea of what it is, and we will stop right here, and we will look at the calculations on Wednesday.